Welcome to the second video on the Module 1 semiconductors. So in this video, we will be discussing about energy band. So in the first video, we have discussed what is meant by atomic bonding what are the various types of atomic bonding like covalent, metallic and ionic bonding. So here we will be discussing what is meant by energy band. An isolated atom, when it is brought together, it will be to form a solid. There will be various interaction will be occurring as we have discussed in the previous video. Fine. When an atom is isolated, that is when it is an individual atom is taken, it will be having an central nucleus which is surrounded by the electrons. So here this is the central nucleus and it is surrounded by the electron orbit. So the orbit will be named as KLM, and electronic configuration is nothing but the electronic structure of the electrons. So here in this case we can say that it is having 1s2, 2s2, 2p6 and 3s2. So the outermost cell is called as the valence cell, and here it will be having 2 electrons. That is, the valence cell is having, the configuration is 3s2. Fine. Now, what is about the energy? So the energy of the atom is represented as discrete energy states. That is, each cell will be having its own energy level, and it is given here. The y-axis in this graph, the y-axis represents the energy level of the various electrons which is present in the atom. Now, when the isolated atoms are brought together to form a solid, there will be, as we know, that there are various interaction occurring between the neighboring atoms. The force of attraction and repulsion between the atom will find a balance at the proper interatomic spacing for the crystal. In this process, important changes occurs in the electron energy level configuration, and this will give us the various electrical property of the solid also. Here we take an crystalline solid. So normally a solid will be having almost 10 to the power 23 atoms. So here we take an example of only 24 atoms. Here when it is taken as an individual atoms, the energies are represented as discrete energy states, or it is represented as a discrete energy level. But the same thing, when atoms are brought together, we can see that the energies are now represented as energy band. So what is this energy band? How is it formed? To understand this concept, we will be taking silicon as an example. So we know that the electronic configuration of silicon is 1s2, 2s2, 2p6 and 3s2 and 3p2. That is, the total atomic number of the silicon is equal to 14, and hence the valence electron is nothing but 3s2 and 3p2. Here we find out that the energy, the first three levels, that is, we will be calling it as ion core state, and this the last level or outermost cell will be playing a role in forming the energy band. Okay, here in this case, the atomic x-axis is represented by it is represented, x-axis is nothing but the interatomic spacing r. So what is meant by interatomic spacing? That is, when atoms are brought, or when we have two atoms 1 and 2, when they are far apart, then R value is more. When the distance between these two atoms becomes small, then we assume that when it is brought nearer to each other, then this is called as R is very small, R is very less. So in this case, in the first case, when R is large, then the energy level is represented as 1s2, 2s2, 2p6 and 3s2 and 3p2. The same thing when R value is very small, then what happens is, that is, here in this energy levels are converted as energy band. Orbital model of the silicon atom is given along with the energy level of the various electrons in the potential well of the nucleus. Let us focus only on the outermost cell or the valence cell n equal to 3, where two 3s and two 3p electrons interact to form 4 sp3 electrons. Qualitatively, when we see that when electrons are brought together, the application of the Pauli's exclusion principle becomes important. When two atoms are completely isolated and their from each other, so that there is no interaction of wave functions between them. They can have identical electronic structures. As the spacing between the two atoms becomes smaller, however, electron wave functions begin to overlap. The exclusion principle dictates that no two electrons in a given interacting system may have the same quantum state. That is, there must be at least one electron per level after there is a splitting of the discrete energy levels. In a solid, many atoms are brought together, so the splitting energy levels form essentially continuous band of energies. As an example, here we take a silicon crystal from isolated silicon atoms, which is formed of n atoms. Each isolated silicon atom has an electronic structure, as discussed, 1s2, 2s2, 2p6, 3s2, and 3p2 in the ground state. Each atom has available 2 1s state, 2 2s state, 6 2p6 state, 2 3s state, 6 3p state, and higher status. If we consider n atoms, there will be 2n, 2n, 6n, 2n, 6n state of type 1s, 2s, 2p, 3s, and 3p respectively. As the interatomic spacing decreases, the energy levels split into band beginning with the outer cell. As the 3s and 3p band grows, here as the interatomic spacing between the atoms gets reduced, they merge together to form an 3s 3p band, which consists of 8n states. And as still R decreases, the spacing between the electron reduces, the band tries to divide into two bands. One is called as the conduction band, which consists of 4n state, and the other one is called as valence band, the lower valence band, which will consist of 4n state. And the valence band will be having the 4n electrons here, and the conduction band will be having 0 electrons. So apart from the low lying and the tightly bounded core levels, that is the lower level here, so the silicon crystal will be having two levels, that is, one is called two energy levels. One is called as the conduction band, and the other one is called as the valence band, which is separated by a gap which is called as the forbidden gap. Since it in a perfect crystal it contains no electron energy state, it is called as forbidden energy gap, or it is called as a forbidden band. Here, the lower 1s band is filled with 2n electron, which originally resided in the collective 1s state of the isolated atom. Similarly, the 2s band and the 2p band will have 2n and 6n electrons in them, respectively. However, there were 4n electrons in the original isolated n is equal to 3 cells, that is 2n in 3s state and 2n in 3p state. These 4n electrons must occupy in the valence band or in the conduction band in the crystal. At 0 degree Kelvin, the electrons will occupy the lowest energy state available to them. Hence, in the case of the silicon crystal, there are exactly 4n state in the valence band and 0 electrons in the conduction band. So every state in the valence band is filled, while the conduction band will be completely empty of electrons. As we will see, this arrangement of completely filled and empty energy band has an important effect on the electrical conductivity of the solid. In this case, when 6 hydrogen atoms are brought together, so we know that each hydrogen atom will be having a valence of 1 electron. So the 6 valence electrons will be occupying the 1s state, which when brought together will be having 6 energy levels as the separation between the atom decreases. Similarly, in the case of sodium atoms, we can see that the energy band will be 2n for the K cell, that is 1s cell, and 2s are 2n electrons in the 2s state, 6n electrons in the 2p state, and then it will be having 1 electron in the 3s state. So here the band is partially filled and it is only half filled, and hence it is called as a monovalent. And here this 3s is nothing but the 3s band is nothing but the conduction band of the sodium. As a recap, in this video, we have discussed about energy band. When isolated atoms are brought together, so the energy level or the discrete energy levels will be represented as energy band. How this energy band is formed, and because of this energy band, what is meant by valence band and conduction band we have discussed. So the formation of the conduction band and valence band and the occupancy of the electrons in these two bands will result in metal, semiconductors and insulators, which will be discussed in the next video. Thank you.